AP Calculus AB, Unit 5, Review, Corrective Extra. So this is an extra worksheet, not required for the retest, but extra credit and good practice. So just a little more practice if you're looking for a little more practice. So let's do these. We're trying to find the derivatives. So this is, I'm going to think of this as 2x to negative 1. We have a product rule here. So we're going to do f prime of x equals x squared times the derivative sign is cosine. Leave the inside the same, times the derivative of what's inside, negative 2x to negative 2, plus sine of 2x to negative 1 times the derivative of x squared is 2x to the first. So we're just going to rewrite this a little nicer. The x squared and the x to negative 2, that gives you x is 0, which is 1. So we can do, say, negative 2 cosine of 2 over x, no negative exponents in my final answers, plus 2x sine of 2 over x. And all the other stuff should end up in front of the trig expressions just to look nice. This one is to the 1/2 power, and there was a problem kind of like this maybe on the test that a lot of people kind of made some funny mistakes on. So, when you do the derivative of this, you're going to do the outer derivative first. Everything inside stays the same. And then decrease it by 1. And then we're going to multiply by the derivative of what's inside, which is the sine, but what's inside of it stays the same. There's no x right here. This sine is inside of another sine. And then the derivative of what's inside that is going to give you another cosine. Final answer, no negative exponents. This stuff's all going to be on the top. So you're going to have, it just depends on what order you want to write it, but there's going to be a cosine x and then a cosine sine x. Some people are like, oh, this is cosine squared. No, it's not cosine squared. These don't have the same thing inside of them. Over 2 square root sine x. The same thing. Sine x is not sine squared. Okay. This one I think would be easier to do like this. To the negative 1/2 and not do quotient rule. So the derivative is going to be negative 1/2 x to the 4th plus sine x cubed to the negative 3/2, and then you're going to multiply by the derivative of what's inside. Now, this is chain rule. It has multiple terms. You better put parentheses around this. 4x cubed plus cosine x cubed times derivative of what's inside. 3x squared only multiplies that term right there. Final answer, this is going to end up on the bottom because of negative exponent. This is all going to be the top. But there is a negative right here that we could just distribute to everything. Negative 4x cubed minus 3x squared cosine x cubed all over 2 square root. Well, I probably won't do a square root. I'm going to do x to the 4th plus sine x cubed to the 3/2 power. And you could do a square root. You could do square root and then cube it, or it's fine if you just want to leave it to 3/2. But no negative exponents. Okay, number 4, find the 53rd derivative. So there must be a pattern. Let's show that pattern to support our answer. The 0th derivative is that. First derivative is negative cosine x. Second derivative is positive sine x. The third derivative is cosine x. And the fourth derivative is negative sine x. And we're back to where we started. I'm going to repeat it. So this is the pattern. So it's groups of 4 and it repeats. So let's figure out how many full groups of 4 we can take out. And the remainder is going to be the clue as to what is left. So 4 goes into 5 one time. A long division, 4 goes into 13 3 times. And the remainder is 1. So if it went in perfectly, and the remainder was 0, you'd just be back at the beginning. The remainder is 1, so it's going to be the 53rd derivative is going to equal negative cosine x. It's going to be the same as the first derivative. So that's the work you could show, unless you really want to do 53 derivatives. This is way less work, but this is the work you could show to support your answer. You need it. You need to support your answer. 53rd derivative of this one, well, again, this is the 0th derivative. First derivative is negative sine 2x times the derivative of what's inside. And then the second derivative is going to be negative cosine 2x. Now we already have a 2, and then we're going to get another 2. And I'm purposely leaving it like this right now. The derivative of negative cosine is going to be positive sine. Leave the inside the same. Now we already have a 2, and now we're going to get another 2. The fourth derivative is going to be cosine 2x, and we already have a 2, and now we're going to get another 2. And part of this pattern is that we're back to where we started with here, but the 2's are going to continue to add up, right? Now here's the thing. This actually had a 2 to the 0th power, first power. This had a 2 to the 2nd power. This has a 2 to the 3rd power. This has a 2 to the 4th power that matches the derivative you're at. So the first thing we need to do is do 53 divided by 4 to figure out the negative, positive sine, cosine part. That's one part of it. So this remainder right here tells you, oh, well, it's going to be negative sine 2x, but then the 53rd derivative is going to have so it's going to be negative 2 to the 53rd power sine 2x. I'm okay with you leaving it as a 53rd power. I don't need 2 to the 53rd power. So there's two different kind of patterns going on there that you got to keep track of. Table problems. You want to find the derivative too. Let's find the derivative first. Don't plug the value in yet. You could do quotient rule, or you could do it like this, which would probably be a lot easier. I mean, either way. I mean, I'll just go and do quotient rule. Maybe I'll try both ways. Low d high minus high d low all over low squared. I mean, it's not that bad as a quotient rule. That term goes away. So then if you want k prime 2, you're going to get negative 24 times g prime 2 over g2 squared. Now, you got to look up these values from the table. G prime 2 is 2, and g2 is 3 squared. So this is going to be negative 48 over 9, negative, take 3 out of this, right? 16 over 3, be k prime 2. Alternatively, we could have done it this way, and so then k prime of x would have been negative 24 gx to the negative 2 times the derivative of what's inside g prime x. Now, if we rewrote this nicely, that would give you negative 24 g prime x over gx squared. Guess what? Same thing, right? So then you get the same answer. So that's an alternative approach. Okay, this one, we're going to have to do product rule and chain rule. Let's find m prime x first. So product rule, x squared times the derivative of f, leave the inside the same, and then multiply by the derivative of what's inside, plus f of 2x minus 4 times derivative of x squared is 2x. So that's the derivative. We could write it nicer first if you want. This is 2x squared f prime of 2x minus 4 plus 2x f of 2x minus 4. And then we're going to plug 3 into this. So if you plug 3 in this, that's going to be 2. And you plug 3 into this, that's going to be 2. So this is going to be 18 times f prime of 2 is 0. F of 2 is 4. So that term goes away, and we get 32 for our final answer. But I made a mistake. Shoot. 2 times 3 is 6. Oh my goodness, 24. So I would have lost a little bit of points for that, but hopefully my work was very clear so the grader would identify my mistake quickly also. Find all the horizontal tangents of this. That'd be slope equal to 0. So we've got to find an expression for the slope g prime of f of x. Take derivative of the outer function first, leave the inside the same, and then multiply by the derivative of what's inside. And then we're going to set equals 0. And the zero product property from algebra 1 says if this factor equals 0, that should give you a solution. And if this factor equals 0, that should give you a solution. So we're probably getting more than one answer. What would you plug into G to get 0, G prime to get 0? A 3. And then you'd say, okay, well, that means f of x has to equal 3. What would I plug into f to get 3? I'd plug x equals 1. So that's an answer. And here you'd say, well, what would I plug into f prime to get 0? Well, there's actually two values, 1 and 2. Your final answer, we should just list, each answer once. So that's the work to show for that. Okay. On to the back. For some a little bit tougher problems. Find k if y equals x is tangent this. So we have a curve and a tangent line. This is a very generic drawing. They share the same point at the point tangentially, and they share the same slope there. So we have two things that we can use to help us. If they share the same point, that means their y's are equal and their x's is equal. Well, if their y's are equal, I have a system of equations, and substitution is super easy because they already both solve for y. So they share the same point. They share the same slope. Well, y prime of this one is 4x cubed, and y prime of the other one is 32. And we're going to set these equal. So 4x cubed equals 32. Now, we can find x right now, even though we're trying to find k. If we find x, then we can plug in here and find k. So we need to find x first. So we're going to solve for x. X cubed equals 8. Cube root of both sides. Do we do plus or minus? Nope, because it's an odd root. But if it was an even root, you better do it. You get multiple answers. So x equals 2. We're going to now plug that in up here. So that's going to be what? 16. This is going to be 64. We'll subtract 16 from both sides. K equals 54. There you go. 10. Find all x on 0 to pi for which this has a slope of 1. So I think like on the test it might have been the horizontal slope or slope of 0. We could do it for anything. So slope equals 1. Got to find derivative. Derivative of sine is cosine. And there's a negative. Leave the inside the same. Don't forget the chain rule. Times derivative of what's inside. And then we're going to set it equal to 1. So now we have a trig equation to solve, which we should be really good at. So it's going to be 1 divided by negative 2. It's going to be negative 1/2. Alpha equals pi over 3. Do not do degrees. You need to get good at radians. It's going to cause problems for you if you don't. Pi over 3, because I have the values for cosine memorized. 1, root 3 over 2, root 2 over 2, 1/2, 0, pi over 6, pi over 4, pi over 3. What quadrants? 2 and 3. So 2x equals, quadrant 2 would be 2 pi over 3 plus 2 pi k. And quadrant 3 would be 4 pi over 3 plus 2 pi k. And then we're going to divide by 2. And we're going to get x equals pi over 3 plus pi k. And x equals 2 pi over 3 plus pi k. And so we're going to get x equals pi over 3, 4 pi over 3, 2 pi over 3, and 5 pi over 3 as x coordinates where this graph has a slope of 1. There you go. And by the way, in my head, I was doing this. I was thinking if I add pi, that's the same thing as 3 pi over 3, right? If I add pi, that's 3 pi over 3. And I expect to get 4 answers. I would usually expect to get 2 from 0 to 2 pi for the 2 different quadrants. But because the 2 inside is cutting the period in half, I'm going to get double what I normally get. Okay, number 11, implicit differentiation. So we're just finding, let's see, 2y dy dx plus cosine xy squared. Now we got to take the derivative of what's inside, so that's a product rule. So that's going to be x times the derivative of y squared. It's 2y dy dx plus y squared times derivative of x is 1. And we got to distribute all that. We got to distribute this to both those terms. Equals derivative of x on the right is 1. So we've done the derivative. Now we just got to clean it up. 2y dy dx plus 2xy cosine xy squared dy dx plus y squared cosine xy squared equals 1. So I just kind of simplify things. Now I want to solve for dy dx, so I need to factor it out of these two terms and then move the other non-dy dx terms to the other side, and then divide both sides by this. The only way we're going to be able to reduce anything is if there's something you could divide out of everything on the top and everything on the bottom, but I think this is it. This is as good as it gets. No negative exponents, no fractions or fractions, it's reduced. All right. Now, finding the second derivative, well, I don't even want to try it with this one. It'd be so bad. I don't think I'd give you something that bad because taking the derivative of this is going to be a really ugly quotient rule. But you would want to get dy dx by itself before you went on to the second derivative implicitly. Number 12, find all the equations of vertical tangents. So vertical tangents, slope is undefined, but is specifically undefined because of division by 0. You have undefined slopes because the slopes don't agree on both sides. That's a different issue, a corner, a cusp. This is a vertical tangent. So we need to take the derivative. Dy dx plus sine 2y 2 dy dx equals 1. I'm going to factor the dy dx out. 1 plus 2 sine 2y. And then finish solving for dy dx. And so that equals undefined, which is going to be 1 over 0, right? So it's the bottom specifically that's going to give us the answers. So we're going to solve the trig equation. -1/2 alpha equals pi over 6, quadrants 3 and 4. So we're going to have 2y equals, quadrant 3 would be 7 pi over 6 plus 2 pi k, and quadrant 4 would be 11 pi over 6 plus 2 pi k. And we divide by 2. Get y equals 7 pi over 12 plus pi k, and y equals 11 pi over 12 plus pi k. Now here's the extra hard part of this problem. There is no restriction on the x or y values, which I wouldn't do to you, but let's see if we can pull it off here. So I mean, really, these are the y values. We're not going to write any more specific ones. There's infinite possible y values, but now this isn't the answer. These are the y coordinates of where the vertical tangents are happening. It's the x coordinates, though, that are going to give you the equations of the vertical tangents. They're vertical lines. So vertical tangents mean we need vertical line equations, which should be x equals a number, right? So we got to plug these back in the original equation to find what the x values are. So let's see if we can do that with this pi k stuff in there. I think we could. It's gonna be a little annoying. So if we plug that in, 7 pi over 12 plus pi k minus cosine of 2 times that. So that's going to be 7 pi over 6 plus 2 pi k equals x plus 1. So then we're going to solve for x. Solving for x isn't going to be that bad, but it's going to be kind of ugly. So anyways, cosine of 7 pi over 6 plus 2 pi k, that's going to be the same answer every time, right? If you add 2 pi k, that's that's a coterminal angle. Cosine of 7 pi over 6, that's a reference angle of pi over 6. It's quadrant 3. So it's going to be root 3 over 2, and it's going to be negative. So this whole thing is going to equal that every single time. So x equals 7 pi over 12 plus root 3 over 2 minus 1 plus pi k. So that's a whole chunk of vertical tangents, and where k equals an integer is the more technical way of writing that, because usually I'm lazy about that. It's just in the middle of my work. And then the other one is going to be 11 pi over 12 plus pi k minus cosine of, if we multiply that by 2, that's going to be 11 pi over 6 plus 2 pi k equals x plus 1. Now this is alpha equals pi over 6. We're quadrant 4. So it's going to be root 3 over 2. It's going to be positive, this whole thing right here. So if we solve for x, we're going to get x equals 11 pi over 12 plus root 3 over 2 minus 1 plus pi k, where k equals an integer. Now, let me just emphasize, I'm not going to make you give infinite answers like this on a test or retest, but it's good practice. You used to have to do this kind of answers all the time in Algebra 2, pre-calc probably. I would give you some restriction in the original problem that would limit the number of answers, which would probably make it a little nicer. But anyways, that was some good practice. I hope that helped a little more. Help you get ready for your retests. So make sure you're ready